Hello, we are going to go over molecular properties and acid strength. I'm going over this with the assumption that you've completed the POGL that I posted, because this is going to tie right into it. So this is really just a summary of what you should have gotten from the POGL. So if you haven't done that yet, just pause this, go back to it, and then go through this. So I'm just going to kind of, again, run through this and summarize it, and then make a couple little notes along the way. And we have one last topic at the end of this that you haven't seen yet that we'll discuss. So acid strength of non-metal hydrides. You saw in the POGL two factors that affect this, the electronegativity of that central non-metal atom and the strength of the bond related to polarity. So you saw two different trends with this. Across a period, the acid strength increases. So that would be something like H2S versus HCl. Okay, as you go across from sulfur to chlorine, the acid would thus increase because of that greater electronegativity, which is going to polar distort the electrons away from hydrogen, which makes it more polar. And then because of that, the hydrogen ion is going to be more easily pulled away by the water molecule. And down a group, acid strength is going to increase. So you saw that in the POGL with HF, HCl, HBr, and HI. So as you go down a group in this case, because the radius becomes larger, that bond length becomes longer and thus weaker, so that hydrogen comes off more easily. So both of these just simply have to do with the fact of what's creating a weaker bond between that hydrogen and that non-metal, and thus going to make it more easily ionized and thus be a stronger acid. All right, you also saw a little bit on the oxoacids, where you have a hydrogen atom that is bonded directly to an oxygen atom, but it's really what's attached to that oxygen atom, what's in the rest of the compound, that has an effect, such as the electronegativity of the central atom that's on the other side of the oxygen, and then the number of oxygen atoms around the central one. So the two things that you saw, one was if you have the same number of oxygen atoms, the acid strength is going to increase with the electronegativity. So in this case, we have with these three, the difference of Cl, Br, and I. And you can see as you go across, because in this case, we're not looking at bond length because the hydrogen-oxygen bond length is the same relatively. We're really looking at just the electronegativity of those atoms. And thus, as you go across, in this case, you're going to be decreasing electronegativity. Okay, which then is going to cause the bond between oxygen and hydrogen to be less distorted, which is then going to create a stronger bond as you go across, which is then why you're seeing over here, you have the weaker acid. Okay, because of a stronger oxygen-hydrogen bond in that case. And you can see a couple other related examples there. Now, if you do have a different number of oxygen atoms, the acid strength increases with the number of oxygen atoms. And again, this has to do with the fact of those extra oxygen atoms are going to pull electron density away from that central atom, which is then going to cause the POGL referred to it as that inductive effect, which makes that oxygen-hydrogen bond more polar. So you can see that as, in this case, when you go across, you're increasing the number of oxygen atoms. Okay, so that by the time you get over on the right here, you have the strongest acid. Okay, because again, as you pull more electron density away from that oxygen-hydrogen bond, it's going to weaken that bond and thus make hydrogen more easily ionized. Here's just a graphic just to explain those two examples with the oxoacids that you can go through. So that just summarizes the big points from the POGL. Definitely important to note, and hopefully by doing both the POGL and just a quick little review, you know, it's clear and understandable. One little thing that they throw into this section in the textbook has to do with aqueous solutions of certain metal ions become acidic because the hydrated metal ion transfers a hydrogen to water. This happens when that metal ion is small and highly charged. It's able to kind of distort that electron density within the water molecule and thus cause it to be ionized. So here's kind of the general reaction where you have a metal ion, it's surrounded by a certain number of water molecules. As it distorts the water molecules, one of the hydrogens in a water molecule, the bond is weakened so much that the outside water molecule is able to pull that hydrogen away from it and thus ionize it. So this reaction ends up producing the hydronium ion in solution, which is important when we go to talk about hydrolysis of salts later in this unit. You're going to see a couple examples related to this. So you have to be able to understand and write this equation and know that those metal ions are going to produce a slightly acidic solution. So this happens with salts of most metal ions that produce a +2 or +3 ions, because again, it has to be highly charged in order to distort the electrons in the water molecule enough. So you can see here's kind of the two steps where you had aluminum nitrate that's placed into water. The nitrate ions are aqueous as well as the aluminum ion, but it becomes kind of hydrated, forms that hydration shell of the water molecules, and thus as it proceeds, one of those water molecules again is going to be able to get that hydrogen removed because of that distortion from the aluminum, and then again creating hydronium. And then this is just kind of a chart that illustrates that as well, to help you visualize it, that you can pause and look at. There's an appendix right in your textbook or online textbook that goes through the Ka values of the various ions, and obviously shows you their formulas when they're hydrated. All right, this would be a good chance for you to just quickly pause and try out these questions just to test how well and check in with what you know, and then I'm going to go ahead and give you the answer. So again, just pause it. All right, for 18.89, we're choosing the weaker acid. So you should have chosen H2SE, and B, you should have chosen H2SO4. In both of these cases, that central atom has a lower or weaker electronegativity. And again, that's based on the Se or sulfur. And then in choice C, you should have chosen H2SO3 because of the fewer oxygen atoms. In 18.90, you were choosing the stronger acid in the following pairs. So you should have chosen in A, H2Se. And then in B, you should have chosen the boron compound. Both of these are because of, sorry, it shouldn't be writing weaker. It should be greater electronegativity. And then in the final choice there, you should be choosing the one with the 2 oxygens because it has more oxygen. So it's going to create a stronger acid. And then if you did look up at Appendix C, which was just in the slide before, because these are all the same concentrations, we can just use their Ka values. So just based on Kas, we would have the 0.5 molar aluminum bromide and then the tin chloride solution. In both cases, they have larger Ka values, so it's going to be more acidic. Okay, produces more hydronium, so it's going to have a lower pH. Okay, that's it.